Hi everyone, in this video we are going to be talking about functions. So we have a lot to say about functions, so we're actually going to split this into quite a few videos. So in this first video we're going to be describing a relation and determining whether a relation represents a function. And then in the next videos we'll do these other objectives. So getting started, what is a relation? Because we need to know this before we can talk about functions. You've probably heard the word function a lot in math. But we need to know about a relation first. So, by definition, a relation is a correspondence between two sets. A lot of times, one set is called X, the other set is called Y. And then the set that we start with, and we'll get into this in more detail, is called the domain. It's basically the input set. And then the set that we end with, like the output, is called the range. So in a relation, each element from the domain corresponds to at least one element from the range. So this is the very formal math definition for a relation, but sort of think about what you know about this word outside of math, and that'll help you understand whether something is a relation or not. This is the key part to it though. At least one element from the domain corresponds to an element in the range. Okay, so let's go forward. If X is an element in the domain, think of the domain as just like a set, a starting point. Okay, so this right here would be, if I circle these, I'll call this the domain. So this is like my bag of X's. I just grouped them together. So that's my domain. And if X is an element in there and Y is an element in the range, the output's down here. Okay, this is like a bag containing Y's. And if a relation exists from X to Y, we say that Y corresponds to X, or another way is to say Y depends on X, and we write this arrow going from X to Y, and that's the relation. So pretty much what you do here in this little machine or part here is the relation. You plug in an X, it does, something happens to it in here, some math stuff, and then out comes a Y, and then X goes in, out comes another Y, and that is a relation. Okay, think of it sort of like a vending machine. You put money in, type in a code, and you get out a snack. Okay, so that is a relation. And so it is often helpful to think of X as the input and Y as the output. But remember, domain for input and range for output. You want to start to know those words. Okay, so a relation can be expressed verbally. A relation can be expressed numerically, using a table of numbers, or by using a set of ordered pairs. So these are just different ways that you're going to see a relation in math. So it can be expressed graphically by plotting points. It can be represented as a mapping by drawing arrows from the domain to the range. Okay, so the relation can be all these things, and we'll go through a few examples next. But this last one here, notice that everything on the left, this teal colored circle, are the domain elements. So this is the domain set here. And then what comes out when you plug it into the relation is these range elements. In this case, it's time is the input and height is the output. So this could be something, this relation that takes these numbers on the left to these numbers on the right. It could be something like a high jump. So how long the person jumped and how high they got, or something like that. So here's an example of describing a relation with words. So a verbal description. The average retail price of gasoline in the US has changed over the years. In 2010, it was for 1 gallon, $2.78. So we know this is very outdated because gas is way more than that right now, especially depending on where you live. So $2.78. 2012, $3.62, and so on. And so it's saying 2018 it costs $2.72. At the time of this video, and where I live, gas is approaching $5 per gallon, just to give it some context. Just a side note there. Okay, so using year as input and price as output, then question, what is the domain and what is the range? And then B, express the relation as a set of ordered pairs. Express the relation as a mapping. Express the relation as a graph. So we're going to do these 4 things. So the relation establishes a correspondence between input, which is the year, so that is our input, and then output, which is the average price of a gallon of gas, so price in the US. So for part A, the domain is all of the years, and so we use these squiggly braces to denote the set. So when you see those, that means in math, the set. So math is a language of symbols. So when you see symbols, they actually can be translated into words. So this is the set containing 2010, 2012, 2014, 2016, 2018. The range is the outputs, which is all the prices of the gasoline. So $2.78 and so on. And then part B, the relation expressed as a set of ordered pairs. So remember, we learned about this when we were talking about graphing, but every ordered pair, the order matters. X is always first, Y is always second. And so X is our inputs. So let me just write this off to the side here. The input goes first, and then the output is listed next to the input that it came from, and that is our Y value. So notice we have 1, 2, 3, 4, 5 set ordered pairs here in our set. So input is the year, output is the gas price, and we do that for all 5 years. And then part C, as a mapping, we're going to use T for the input year and then P for the output price. And now notice the year column, you can say, is in order, so it's descending. And so what happens is the arrows kind of can look crazy depending on what you do with the price column. The price column is also descending, ascending. It's getting bigger as we go down. So because we're trying to keep this in order, that's why these arrows look kind of crazy. But if you wanted to, you can just put, like, for example, 278 up here, and then your arrow would go straight across like that, and so on. But we wanted to stay a little bit more organized, so that's why those arrows look like that. Okay, and then the last part, this is the graph of this relation. So notice that the horizontal axis, which is our x-axis, we've labeled it as T for years, for time, and then the y-axis is labeled P for price, and then every ordered pair gets a point. So in 2010, the price was $2.78, which is about right here, and then we have a point at that location, and we do that for all 5 input and output values. All right, so now that we learned about a relation, it's going to lead us right into a function. So if you feel okay about what we just talked about, then knowing what a function is going to come naturally to you. So let x and y be 2 non-empty sets. A function, which is what we're defining formally here, from x into y is a relation, that's why we had to learn about that, that associates with each element of x exactly 1 element of y. Okay, just this little asterisk right here. Usually our sets are working with real numbers, but we can also work with complex numbers and other things. So, but just for now, especially in college algebra, you're working with real numbers. So the key thing to actually notice on this one is that to be a function, we have to have exactly each element of x match up with exactly 1 element of y. I mentioned this earlier, but think of a vending machine. If you have your money, you put it in the vending machine, you type in your code, and you got 2 snacks. 2 snacks came out. Yay! You'd be happy, but the machine's broken. It's not a function. It's not functioning. So put one thing in, one thing comes out. That is a function. All right, so let's just talk a little bit more in detail about domain and range real quick. There's quite a bit here, but what I want you to focus on is that domain is input values, what you plug in, and range is the outputs. There's also this term called the image of x. That's just saying that if I have something in the range over here, it is the image of where it came from in the domain. So if, like my vending machine, this would be like Snickers, and it was the image of money because money is what was plugged in. There's this idea here also that sometimes there might be some values in our this output set we're calling y that aren't part of the range, but you don't really have to focus on that. What you want to focus on is like these two teal colored ones. The domain gets plugged into the function, those values, and the output is just these range values right here, just this part, what comes out from plugging stuff in. Okay, so example, for each relation, state the domain and the range. So this is going to give us some practice on identifying the inputs and the outputs. Then determine whether the relation is actually a function or not. Because remember, it might be a relation, but it might not be functioning, like our vending machine example, so it won't be a function. So first one, the relation shows the correspondence between an item on Puffy's Taco food truck and its price. So we have menu items and then the corresponding price for those items. So beef taco, chicken taco, shrimp taco all cost $2.50. Quesadilla is $4, nachos is $5.50. Okay, so the domain is the set containing all the menu items. Notice we have our squiggly braces and we have listed all of those menu items. And then the range is the output or the price. So if we pick a menu item, then we have to pay this price for that. So notice that even though there's 5 inputs, there's only 3 outputs because all of the tacos cost the same price. This is, in fact, a function. It is perfectly fine that one beef taco costs the same price as one chicken taco and one shrimp taco. This is still functioning properly. So even though 3 items in the domain correspond to the same price in the range, that's still a function. It breaks down if the opposite happens. If a beef taco costs like 2 different prices, that would not be a function. Okay, so how about this one? This shows the correspondence between friends and the average number of steps per day recorded on their pedometers. So our friends are here, and then this is the number of steps that they've walked, and then they've tracked it on their pedometers. So the domain is the set of all of the people. So our 4 people are listed, and then the range is all 4 amounts of their steps. This is also a function, and this one's actually called a one-to-one function because they all had different amounts of steps. So this 4610 corresponded to exactly Gabriella and no one else, and so on with the other 3 values. How about this one? This is a correspondence between students graduating from high school and the colleges that these students are admitted into. So take a look at this and then think about if this is a function or not. So Aaron was admitted to Princeton and Duke. Christina was admitted to Stanford, Anton was admitted to Duke, and Jaron was admitted to MIT. So the domain is the people, and the range is the colleges, and then this one is not a function because not every element in the domain didn't correspond to exactly one element in the range because of this one here. So Erin here, because she was admitted to 2 colleges, this like broke the machine. It's not functioning. We have 1 input but 2 outputs. So this is still a relation, in this case between students and college admittance, but it's not a function by our definition of a function. Alright, and then let's do this example here. So now we're working with ordered pairs. So for each relation, state the domain and the range. So again, we're practicing identifying domain and range. This time we're working with ordered pairs though. So remember, input is first, output is second. Input is X, output is Y. Okay, so the domain is all the inputs. So notice it's the set containing 1, 3, 5, and 9. And the range is all of the outputs. Let's underline that in green. 5, 9, 1, and 2. Just written here in ascending order. And then this is a function because there are no ordered pairs with the same first element and then it's like a different output, a different second element. Okay, how about this ordered pair here? So we have the domain is 1, just in order of small to large, 2, 5, and 7. Those are our domain elements. Our range elements are 5, twice, 6, and 15. This is also a function. Even though 5 got repeated twice, it's okay, because if you want to draw it, this will probably help you. And so if you're ever confused, just draw it. If you draw this as the domain elements and the range elements, take a look, it's still going to be a function. So 2 goes to 6, 5 as an input went to 5 as an output, 7 as an input went to 5 as an output, and then 1 as an input went to 15 as an output. This is okay. This is still a function because 2 separate inputs went to the same output. That's not broken. That is functioning. It's broken if one input splits into 2 outputs. So try to remember the vending machine to help you remember that what's the case when it's not a function. Okay, so take a look at this one. And so notice that this is not a function. So our domain elements, -5, -2, 3, 2, and -5. Our output or range elements on this one are 1, 2, 3, -2, and -3. And then watch why this is not a function. It's because -5 gets inputted twice and 2 different numbers are the output. And if you draw it, you will see. So if you want to draw this, and hopefully this just helps you visualize it, you will see that it's broken, it's not functioning. So -5 corresponded to 1, and then -2 corresponded to 2, 3 corresponded to 3, 2 gave us a -2, and then on the last ordered pair it was -5 again, and it gave us a -3. So let me add that into my range here. And so -5 split and gave us 2 different outputs. So this is not a function. We cannot have one input produce 2 outputs. No, we don't like this. So it's not a function. Okay, so let's do this example. Now we're going to be working with functions. So we used a lot of other types of examples, and you're going to be seeing this type of example more often than the other ones. You're going to be actually working with equations and wanting to know, are they functions or not? So this equation, is it in fact a function by our definition? So let's think about it. This says for any x that I input, I'm going to multiply it by 3, and I'm going to add 7 to it. Any number you can possibly think of, when you times it by 3, you're going to get a number. You're just going to get one number. You're not going to get 2 numbers. It might be double digit or triple digit. It doesn't matter. I'm just saying it's a single number. So like 3 times 10 is still just 30. It's one number. Then if I add 7 to it, it's just a single number. So no matter what I input here, whatever gets plugged in, I'm going to get one output out. So I'm going to plug in one x and get a single y. That is a function when you do that. So this one is functioning perfectly fine. You could try some numbers if you want to make sure. But this one is actually called a linear function because it would be a line when you graph it. So this one is a function. How about this one? Is this equation a function where y is a function of x? So let's think about it. We're going to go ahead and try to solve this one for y to help us see more clearly. Because if we can understand y equals in terms of the other things, then we'll be able to know better off if it's a function. So subtract 6x from both sides. That's a weird x. 6x from both sides. Then we will divide by 3. So divide everything by 3. And then notice this is y squared. So if you want to get y by itself, you're going to square root both sides. But whenever you take the square root like this, you need to put a plus and minus. Okay, so plus and minus there. And so think about this. What does this say? This says that for x's that I plug in, right away you can already tell because there's a plus and minus, there's 2 values. Okay. This part here, x is less than 1/3, is just because we want to make sure we have real numbers. Square roots of negative numbers are imaginary. Just a quick side note. These are imaginary. Okay, so that's what that part's for. So any x I plug in, I'm actually going to get 2 outputs. And that is not a function when I do that. So for one input, I'm going to get two different outputs. So this is still an equation, but it does not define a function, because it would be the case where one x gives me two different y's. And that is not a definition of a function. Okay, so that is it for the first part of this video. Thanks for watching. In the next video, we'll be talking more about functions, starting with our function notation. All right, see you soon.